is a talk about the smallest things in the universe. Fundamental particles, the ingredients of all the matter, all the stuff that we see around us. These things are as small compared to atoms as atoms are compared to us. And yet we think if we can identify these fundamental particles and understand their behavior, then in turn we can understand the structure and the behavior of the universe at larger scales still. So, if you like, this is actually a talk about the science of small things, my area of science, particle physics. And in my talk, I'm going to give you an overview of the subatomic universe. I'm going to show you how complete our understanding is, but I'm also going to show you what's missing, because there's one vital piece that we haven't established yet. It's one particle that's been predicted to exist that we've never yet seen, the elusive Higgs boson, or God particle as it's sometimes known. So I'm going to show you in this talk why this tiny esoteric particle is of such significance for our subject that it drives our research in particle physics. It really does represent the cutting edge of what's going on. And I'm going to show you our latest experimental results so you can see for yourself just how close we might have come to seeing this elusive particle. But let me start off by describing the subatomic universe first of all. It's very simple. Everything we've seen is made of the same basic type of building blocks, and there are 12 of them. 6 of a type we call quarks, and 6 of a type we call leptons. And what makes matter is a small number of forces that glue these ingredients together to make the universe look the way it does to us. There's the weak force, responsible for radioactivity. It acts on everything. It's conveyed by force-carrying particles, W and Z bosons, and I'll say a little bit about how that works in a moment. There's the electromagnetic force, most familiar to us in everyday life because it's driving the projector, the lights, my laptop, everything. It acts on anything with an electrical charge, so it acts on all charged fundamental particles, conveyed by photons of light. And quarks, in addition, feel something called the strong force, which keeps atomic nuclei stable, because it's an attractive force, and it overcomes the electrostatic repulsion between the positively charged protons inside the nucleus. And that is basically it for particle physics. Those are the ingredients of our universe. It is simple. However, it's not the whole story. As ever, there is one more fundamental force that's extremely important. That's gravity. Gravity is responsible for the large-scale structure of the universe. It acts on mass, and it should act on every single fundamental particle, because we know they have mass. We've measured that experimentally. But gravity is so much weaker than the other forces that we tend to neglect its effects. And so in particle physics, we only concentrate on the first 3. So there we have it. There's our ingredients. And we even have a picture for what sticks them together. We think a force is conveyed by means of an exchange of a force-carrying particle between matter particles. And we can encapsulate this interaction in mathematics to form equations. And these equations form the basis of our theory of particle physics and the subatomic universe. And this theory is really, really short. It's really succinct. So short, in fact, that you can write it on the front of a T-shirt. And you can buy the T-shirt if you even want to. I must admit, it's one of my nerdy tendencies. I would like a T-shirt like this. I just haven't allowed myself to have one yet. It's so short because of the mathematical structure that we believe the universe has. We believe that every force we can describe behaves in the same way, and thus we can write the equations to cover them all equally. The universe is simple. It's symmetric. The maths is elegant, it's even beautiful. But more than that, the theory is fantastic because we haven't yet made an experimental measurement that disagrees with one of its predictions. It's so good that we call it the standard model of particle physics, which is great, but there's always a but. And the but is we know that this theory isn't complete. There's more to understand. The theory doesn't contain gravity for a start. And that's because we don't know how to describe gravity in the same way as everything else. It just doesn't work. It gives us rubbish. Also, the theory lacks explanation for many of the fundamental properties of the universe we'd like to understand, like dark matter, dark energy. We have no idea what those are. Even more worrying is the fact that we don't even know if the theory is right at all. It could just be very good at predicting what we see in experiments and come from a completely wrong standpoint. And that's because of the one missing ingredient that I haven't really talked about up to now. And that comes back to this issue of mass. Because the theory I've talked about so far predicts everything to be massless. So in order to describe a universe where we know things are massive and heavy, we have to add an explanation of why fundamental particles have their mass. And there is at least a theory that tries to explain why this is, not a new theory. It was first put forward in the 1960s by many people, amongst whom was a man called Peter Higgs. And this theory tries to explain mass as something, a fundamental property a particle gets by means of its interaction with something called the Higgs field. Now, this is just an energy field which pervades the universe. It's present everywhere. And we think that a particle gets its mass as it moves through the universe, and the amount of mass it gets just depends on how strong its interaction with this energy field is. So that if, for example, you are a photon of light, which is massless, you don't even see the Higgs field as you move in the universe. But if you're a very massive, heavy particle like a top quark, then moving through the universe is like moving through treacle because you're interacting a lot with the Higgs field around you. Now, we don't see the Higgs field, it's completely invisible, but we could see the particle that's predicted to accompany it, and that's the Higgs boson. It's a particle that we should be able to produce in our particle physics experiments and collisions, and we should be able to detect it in our experiments by the characteristic way it decays and leaves a topological signature. However, unfortunately, until now, well, not even now, we haven't seen it. And this is a real problem, because if we don't see the Higgs, then we can't be sure that it exists. And if the Higgs doesn't exist, then this theory that I've just been talking about is completely wrong. And if this theory is wrong, then so is the standard model, because this theory is actually an integral part of the standard model. It's needed to make the predictions make sense, because if it's not in the standard model, the universe that the standard model describes is a very different one. It's one where nothing has mass. It's one where electricity and radioactivity behave very differently, where you don't even have atoms. So it describes a universe, yes, just not our own. And, well, if there's no Higgs, then we just don't understand a thing, basically. And it's for that reason that looking for this particle is of such enormous importance to particle physicists, because it's the only way we have of verifying if the approach we've taken to understanding the universe is correct or not correct at all. It's the only way we can find out. Now, you may also have heard about the Higgs by its more common nickname, the God particle. And I have to say, this is a term that particle physicists hate. We absolutely detest it. It's just because Herb suggested such a lovely title for my talk that I was compelled to use it. So here comes the explanation. So the nickname, the God particle, actually comes from a book written by Nobel Prize winner Leon Lederman in the 1980s, entitled The God Particle. Now, not even Leon Lederman, who's had an awful lot of stick from the particle physics community for doing this, wanted to call the book this. He wanted to call it the Goddamn particle, because this book described the frustration for the search for this elusive particle, looking for it everywhere, not being able to find it. However, his American publishers persuaded him not to use the word goddamn and to have something a little more catchy as a title. That's where it comes from. However, I have to say, although I hate this as a phrase, it does have some strange degree of appropriateness in our theory, because inside the standard model, the Higgs is something that we always say is ubiquitous throughout the universe, but it's also responsible for the way the universe has turned out. As I've said, if it wasn't there, we wouldn't be here either. That's about as near as I want to get to the term the God particle. It's got no further connotations than that. Now, this was a book written in the 1980s, but nearly every particle physics facility since then has been avidly looking for the Higgs. It's one of the prime questions that we're trying to answer in our research. Everywhere you go where there's a particle physics set of experiments, particle physicists are trying to look for the Higgs. It must occupy at least half of the world's community. It really is a tremendously important problem to solve. the reason why it's taken us so long is that although the standard model predicts how the Higgs behaves for us very nicely as a function of how heavy this Higgs particle is, it doesn't actually tell us how heavy it is. So we're faced with a whole set of possible signatures for this particle that just depend on what mass it might happen to have in nature, for which we have no information whatsoever. And that means when you devise a strategy for trying to find this particle, well, you have to try every single combination. It involves a huge amount of data analysis and data mining. Now, very recently, the search for the Higgs has shifted to our newest particle physics facility, and that's based at CERN, the European Centre for Particle Physics. It's the Large Hadron Collider, or LHC for short. And this is an amazing machine. It's huge scale, it really is. It occupies a circular tunnel 27 kilometers long on the French-Swiss border. So in my crummy aerial photograph, to put it in context, you have the Alps here, Lake Geneva, the city of Geneva, and the French-Swiss border is somewhere wobbly in between here. It's 100 meters under the ground. You can go and visit it if it's not operating, and if you do, you'll find yourself standing somewhere like this. It's a tunnel which is so large that you can just see the curvature stretching away in the distance. You're just aware of it. What you're more aware of is that you're standing in something perhaps the size of a London Underground tunnel, if you've been down there, although it's a lot lighter and a lot cleaner, and things in it generally move a lot faster than they do in the London Underground as well. Now, what goes on when the LHC does operate is that we have two beams of protons, that's the nuclei of hydrogen atoms, circulating in opposite directions around this ring. And we accelerate them using magnets to enormous energies until at design spec, these protons will be going just 20 kilometers an hour less than the speed of light. Amazing. And when we have them going that fast, we bring them into collision at 4 points around this ring where we build our experiments. And with those experiments, we take a snapshot of what goes on inside a proton-proton collision. Now, why the LHC is so interesting and so notable is that it's the most powerful particle accelerator that we've ever built. It's so powerful that inside these proton-proton collisions, fleetingly, for the tiniest instant of time in the tiniest area of space, we recreate the very hot conditions of the extremely early universe when matter last existed as free fundamental particles. That's why we do it, to study them. Now, by extremely early, I don't mean days old or even hours old. I'm talking billionths of a second old. That is what we try and simulate inside each collision. And we don't do this once or twice with the LHC. We do it 40 million times a second. It's a huge undertaking. No less huge are the experiments we use to make the measurements. I'm sure you've seen this. It's a picture of the Atlas experiment taken during construction. And it's just nice because it gives you the sense of scale if you compare it to a normal-sized person in front of it. This is the size of a 5-story building. This volume is now completely filled with precision particle detectors that we use to detect what goes on inside a collision. The other experiments are equally large. Somewhat weird when you bend your mind around the very tininess of the things we're trying to study. This is a picture of the CMS experiment, again taken during construction. These two halves are about to be joined together. The C, by the way, stands for compact. It's a very relative scale because it's slightly smaller than Atlas. And the other two experiments, ALICE and LHCb, are of the same scale too. So what goes on is that when we have this is a real particle physics animation here. When we have protons colliding together, in that collision, we generate fundamental particles that fly out from the collision point with huge energies. With our experiments, we can measure their paths and make measurements of their energy. If we read out this information and digitize it and store it electronically, we can analyze it offline. If we compare it to our theory, we can infer what fundamental interaction went on in that collision, what fundamental particles were produced and how they behaved. And if we do this again and again and again, from a series of snapshots like this, we build up a big picture of what went on in the universe. And from the point of view of the Higgs, we should also be producing that in these collisions, maybe once every hour or two. And our challenge is, if it's there, to distinguish it from the background processes that look extremely similar, but which happen to be produced many millions of times more often. So, what have we seen? The LHC has been operating really, really well. We've had about 350 trillion proton-proton interactions delivered, and last December, you may remember that ATLAS and CMS, the two experiments that lead the search for the Higgs, presented their latest results. And wake up. This is what they saw. In fact, it's not quite what they saw. This is even more up to date. It's what was submitted for publication less than a week ago. These two plots encapsulate the entire search for the Higgs in the two experiments. ATLAS at the top, half of the CMS data on the bottom. The thick black line that you can see, the wobbly one, is what we measure in data. It's as a function of the mass of the Higgs particle on the x-axis. And the coloured band in both cases shows you what we'd expect to see if there were no Higgs at all in the data. So the key is, if you see an area where the black observed curve disagrees with our prediction of having any Higgs there, you might have seen something. What was so compelling is that these two independent experiments with independent data observed similar behaviour. Similar behaviour that could hint at the first glimpse of something new in the data with the same mass, about 125 times the mass of a proton. This is extremely strong. We were so excited when we saw this for the first time. What stops it being an observation, though, is the fact that this is only half of the CMS data. If you look at the other half, to other decay modes, there's no evidence of anything. So this is such a frustrating time, because this is as close as we've ever come to being able to answer this very fundamental question in our subject. Is the Higgs there? Is it not? Do we understand the universe? Do we not? Maybe. So you can't say anything yet. We can only answer the question by analysing more data, and that's what's going to happen this year. So this is even more latest news, because last Friday, there was a workshop where the physicists that run the accelerator decide on how they will run the LHC for this year. And they decided to run it at slightly higher energies, but to collect 3 times as much data as we have so far. And this much data should be sufficient to either confirm this glimpse as an actual sighting, or else to confirm that this glimpse is nothing more than a statistical fluctuation, nature being very cruel to us and teasing us with something that looks exciting. So in other words, this year, 2012, it's really the year of the Higgs. At least if you're a particle physicist, it's absolutely the year of the Higgs. It's finally going to be the year when we can deduce whether this God in small things is actually there, or whether it's just a figment of our imagination. Thank you. So this is a talk about the smallest things in the universe. Fundamental particles, the ingredients of all the matter, all the stuff that we see around us. These things are as small compared to atoms as atoms are compared to us. And yet we think if we can identify these fundamental particles and understand their behavior, then in turn we can understand the force, most familiar to us in everyday life because it's driving the projector, the lights, my laptop, everything. It acts on anything with an electrical charge. So it acts on all charged fundamental particles, conveyed by photons of light. And quarks, in addition, feel something called the strong force, which keeps atomic nuclei stable, because it's an attractive force, and it overcomes the electrostatic repulsion between the positively charged protons inside the nucleus. And that is basically it for particle physics, though it's very simple. Everything we've seen is made of the same basic type of building blocks, and there are 12 of them, 6 of a type we call quarks, and 6 of a type we call leptons. And what makes matter is a small number of forces that glue these ingredients together to make the universe look the way it does to us. There's the weak force, responsible for radioactivity. It acts on everything. It's conveyed by force-carrying particles, W and Z bosons, and I'll say a little bit about how that works in a moment. There's the electromagnetic Higgs boson, or God particle as it's sometimes known. So I'm going to show you in this talk why this tiny esoteric particle is of such significance for our subject that it drives our research in particle physics. It really does represent the cutting edge of what's going on. And I'm going to show you our latest experimental results so you can see for yourself just how close we might have come to seeing this elusive particle. But let me start off by describing the subatomic universe first of all, and the structure and the behavior of the universe at larger scales still. So, if you like, this is actually a talk about the science of small things, my area of science, particle physics. And in my talk, I'm going to give you an overview of the subatomic universe. I'm going to show you how complete our understanding is, but I'm also going to show you what's missing, because there's one vital piece that we haven't established yet. It's one particle that's been predicted to exist that we've never yet seen, the elusive